Thank you very much, and it's a great pleasure to be able to talk to you all today. And I've really enjoyed hopping on a plane for 32 hours to get here, and I hope you'll find what we're going to discuss interesting. This morning's discussion raised a series of issues concerning the size of the global population, transitions in how we live, and the general strong trend towards moving to an urban landscape. And it's a fact now that human beings, the majority of human beings, are now living in an urban landscape, and we could arguably redefine ourselves as Homo urbanum, which means urban man. So the challenge for us now is our urban environment, our default human habitat, is it really working for us, and can we make it work better? As the discussion this morning centered on population growth, population pressure, economic pressure, and it's all coming at a time that requires a careful rethink of how we're going to define our human ecosystem going forward. Oops, sorry. Okay, we talk a lot about innovation, so what I'm going to show you today is actually an invention. So it is something that is quite new, and I'm putting this up as a little bit of bragging rights because it took 4.5 years to get a US patent, and I'm very thankful. But this is new stuff. So the interesting thing about the patent application process was that when they were looking for prior art, the citations of the prior art were from 1885. So we have not seen substantial new innovation in urban distribution architectures for most of the last 100 years. And I think that that's been a lacking. We've had industry and technology always refer to dumb pipes. They didn't want to invest in dumb pits and pipes, and consequently, we've seen technology costs fall, we've seen civil costs rise. So we now need to think about what we're going to do with urban distribution. So moving right along, this is about adapting the landscape. And we need to adapt our landscape because one of the big crises we're having at the moment is that there is a terrible lack of global productivity. Productivity is flatlining. Despite technology, we don't see it in the US, we don't see productivity growth in Europe, and we're not seeing it in the advanced economies. Places with a lot of digital capacity, like South Korea, are flatlining in productivity in service industries, all counterintuitive. So we need to start thinking about both the functionality and the economics of the systems that we use in our society, both to manage the environment and to allow our economies to grow and for the quality of life to improve. Currently, our systems are poorly designed. As I mentioned before, 1885 was the reference citation in my patent application. And in fact, we put wires up poles, and we first did that in 1842 with telegraph lines in the United States. In 2,000 years ago, the Romans were the first to bury pipes underground. And essentially, that is still exactly what we are doing today in urban distribution. And so, as we move, I'll give you some examples there. This is hideously inefficient infrastructure. We lose more than 5% of our electricity up poles. We lose 10 to 15% of our water buried underground. When we want a new system, we've got to rip up the streets, and the sheer costs and time delays of adapting the urban environment using these platforms is prohibitive. This is compounded when you have major weather events, which causes local flooding, sewer systems are overflowing, and this is global. It's happening in the advanced economies, it's happening in the third world, and everybody's got to start changing. There's 4 billion people living in cities now, and we have to start doing something. So let's start rethinking from the ground up. And I'll just jump through there. Civil costs, as I mentioned, 60% for broadband, 70% for water systems, 50% for power upgrades, 70% or more if you're moving underground, and stormwater is dominated by civils. And we simply can't afford to be solving problems one by one. In Australia, for example, to dig up the streets of Australia to put one system in, such as the National Broadband Network, the civil costs are around $50 billion. Go to multiple systems, electric cars, grey water, etc., it all becomes cost prohibitive. So, I'll go to a picture. We need pictures, sorry. Here's the invention, the NENA access pathway. So what we're doing is that we're redesigning the curb and gutter. The curb forms the boundary line between the road surface and the pavement. If I say footpath, that's what we say in Australia, and the pavement. So let's reconsider our usage of that space as a multi-utility access system. So the basic elements are, we have on the left-hand side a water channel sitting below the gutter, and that captures road water. If we capture road water and manage it separately, road water is only 15% of urban rainfall, but it carries 90% of the contamination of that urban stormwater. So on the outside channel, we've got what I call the brown water channel, and on the inside, we have the clean water channel. Clean water comes primarily from rooftops, and typically the residential block will be 35% of its surface area will be a roof, which has perfectly good water falling on it. The next channel just inside from the brown water channel is a power systems channel. So now we have at the curb, still tracking around all of our transformers and bits and pieces of the established grid, we've got the capacity to put in 3 different types of network. The one I'm most excited about is in fact an electric car charging network. We can introduce a 480 volt 3-phase power source at the curb. The next is that we can have, which means you can recharge an electric car anywhere, which means over the course of the next generation, we can contemplate that electric cars will challenge the 120 billion litre per annum consumer commute consumption of petrol. So by opening up that market to the electric vehicle industry and making it functionally practical, because we've got quick charging in the garage and quick charging at the curb, we can start to think about gigaton reductions in CO2 emissions. 1 billion tons of CO2 emissions due to urban commutes in the United States alone. The next network we can have is a dedicated microgrid for the management of solar systems locally. What that means is that the solar network doesn't need to go onto the grid. It can have its own grid because we've got a low-cost infrastructure location. This is now a new domain for infrastructure. And so we can start to manage solar in a much more efficient way. If we do that, we open up a new power source within the market, which has the potential to substantially reduce our reliance on fossil fuels. Those 2 initiatives alone, I'm energy neutral so long as it's clean. And what we're seeing at the moment is that we have, last speaker from Dominion basically said there's all these energy sources. And at this point in time, we actually have an energy price war going on. And it's rampant in Australia. Consumers are using less energy, and at the same time, those energy supply prices are going down, but we're seeing a migration and increase in network charging. So competitive energy supply now is going to be dictated by distribution economics, not the thermal efficiency of the source. In Australia, for example, 60% of your electricity bill is now a distribution charge, not the energy source charge. So introducing those things, and then the yellow channel in the middle, the thin one, is optical fibers. And what you see there drawn to scale is 4 fiber lines with 150 fibers each in them, running around a block with 50 households. So unlimited fiber. No issues about the quantum of fiber or fiber access. And this will revolutionize things like the Internet of Things, if that's the way we're going. It will massively increase the potential for data generation, but not generating data is one thing. Using data is what's really important. And so by co-locating both a data source and an energy source and a water source, we gain a whole lot of interoperability options. The next channel is your gas and liquids redistribution. It's very good to harvest water, but if you can't plug it into the now aging and old water distribution system, and you've got to dig up the streets to put a new architecture back in as a separate system because the existing water utility says it's not the same quality mix, then you start to have problems with the basic economics. We're digging up streets for no great advantage. But we also have a channel, so we also have space there for gas systems, so clean gas, so energy, gas, water, information, co-located in a common architecture. And so here's just an example, clean water, dirty water. Let's separate the two, manage them differently. Now we can start to think about the urban environment in a new structural unit, and the one that I've looked at is basically the residential block. My background is naval architecture, and for me, I like sort of things with defined populations and a nice boundary around them, and the fact that it's not floating just means it's not as interesting as a boat. But anyway, so this new block now has a series of dimensional characteristics which are really important to find out. We had to survey 250 blocks in Australia to actually find out what the national average looked like. I did a similar study for California, and I've got the same metrics now. So with that data, we can now look at what the rainfall is. We know the area inside the curb boundary. We can estimate what the annual water input into that block is, and we can separate both the dirty and the clean components. So we're integrating the block as a new, largely water and energy self-sufficient unit, and we'll be looking to integrate those right across the board. The other thing is a lot of people have talked today about resilience, and resilience is we now have to redefine resilience in an environment of uncertainty. As much as we've spent, I think globally now, we've spent more than $500 billion on the problem of climate change, we still have very little hard data to work with. And so we have an environment of uncertainty where we're told things are going to get worse. We don't know how much worse, but we need design metrics. The best way is to say, well, what's the safest place in the urban environment in which we can locate our utility services? And that's what we've done. We've taken the point where there is zero wind by scientific definition, otherwise you're ripping the atmosphere off the planet, and we've removed it from the threats of fire, we've removed it from the threats of flooding because we're managing the flow of water better in the urban environment, and we've removed power lines from the threat of having trees, etc., blow over them. So in terms of resilience, this now looks a little bit like the old First World War, we used to call them slit trenches. So basically on the front line, you got into a little narrow trench and that was the safest place to be, even when bombs and cannons, etc., were going off around you. So from a survival point of view, we've now dealt with those issues very, very specifically. We also have a new economic model because all of a sudden we've got an architecture with a range of functional capacities. So what we're looking at from an economics point of view is economies of scope. If these systems are sharing, so we've got clean roof water is a resource, we can pay households to supply it to us and encourage them to be efficient. We've got road water as a community resource, small volumes, dirty, easier to clean. We're no longer pushing pollutants into riverways. We've got a space for power systems. They're a new class of tenant in this commercial property. Very important consideration. This is commercial property and the layer 2 elements are tenants in it that pay a lease charge. They get a lot of advantages from being there. From the previous slide, there's no weather damage, there's no car crash risk, and the shared capital and operating costs in this environment from all of our research are much, much lower. So everything is working in a known, defined space. We have in the world at the moment a very large number of applications. Clean water, filtration, solar, electric vehicles, etc., smart lighting. What we lack at the moment, though, is an operating system for all of those new technologies to work economically. Big data is great, but if big data is really expensive, then it doesn't really work. Smart cities need smart access in order to function economically and efficiently. So I'll just to give you some idea of the scales. So down at the bottom in the power channel, that's an 11 kV power line. It goes all the way up to 240, 215. Lots of space for fiber, lots of space for water systems, and a feeder, a redistribution channel. That side open channel is where things come out of it, and then the small feeder lines, 2 households come back along, and then they cross the footpath directly. So lots of stuff in one small space. Productivity is central to the economic future of the world. And I'll use this chart to illustrate how utilities in Australia have actually been a drag on productivity growth over the last 10 years. The rise in productivity before that was attributable to the corporatization, where they were required to become dividend-paying, publicly owned enterprises. They did well. We got to around 2000, and we saw a range of activities which basically prices were going up, consumers were using less. If prices rise and consumers are using less, then we're seeing declines and drags on our economic productivity. And we can't afford that. We can't afford it at a national, at a state, or a community level. So we have to think about economies of scope and integration in order to make things work from a financial point of view. I'd like to talk briefly about saving California. From my point of view, I look at California and I think, wow, this is the first global-sized economy to go water critical. And by what I mean by water critical is that they're having to sacrifice the supply of water to one sector of the economy and take it away from another. So even though agriculture accounts for 70% of California's water use, it's accepting a 25% cut. Residential and commercial are accepting a legislated 25% cut. And in that environment, it is very difficult to start to consider how do you build long-term growth and economic security in a state or a country that is drying out. In the city of Sao Paulo in Brazil, they were cutting water 3 days a week. It's a city of over 9 million people, and a lot of them live in high-rise. No water in a high-rise means you've got to go down 10 flights of stairs to find a toilet somewhere. It's an ugly situation to be in, but these are real threats that are taking shape. California is particularly well suited, as is the United States, because you guys love organizing yourself in rectangles. You're the best at it in the world, and I congratulate you for that. But basically, I was able to get a snapshot of over 100,000 households because I could find about 50 locations, all with identical blocks, and they were massive. So there's just some examples there. So what sort of numbers do we get? In California, you've got around 18, 19 inches of rain per annum. That's a population-weighted average. When we're looking at a state level, we need to know how much water people are getting where. So the population weighting is very important. And it gives you an idea of roughly what you can do. But you've got a perimeter of about 626 meters, 2,054 feet. I'm struggling with the old units here, but about 36 lots per block. And roughly speaking, there are 324,000 residential blocks in California alone. So if we adapted California with the NENA access pathway, we'd get a roof water yield, that's at 35% roof area ratio, of around 1.1 cubic kilometers. That's 1.1 billion cubic meters of water, or 1 billion tons, just under 900,000 acre feet. We can clean the road surface water. That's another half a cubic kilometer. Then we've got other surfaces around the block. We can pick up water there. We've got commercial buildings. We can pick up water there. And then we've got leakage reduction. At the moment in California, you're losing around 15, maybe 20% of your water, and that's considered the norm in America. It is not good enough for a water-constrained world to lose that much water. What we say here is let's harvest the clean component, bring your main supply back to that tank, and then we've got a nice, shiny new water distribution system that is surface accessible, highly instrumented because we've got fiber, we've got technology, and we'll pick up any leaks really, really quickly. To put that in perspective, the non-agricultural demand for water in California is 3 cubic kilometers, and through this technology, we've got about 2.7 added to it. So in effect, we've taken the residential urban market out of the political consideration of water. We can then look at adapting the agricultural sector to make it more efficient, and they're already talking about 20 to 30% efficiency gains. So in California, where the rain is not where the primary water supply is. So they rely on snows in the Sierra Nevadas, but Los Angeles, for example, gets a reasonable quantity of rain in a concentrated 6-month period over their winter, but all of it is going to waste. And not only is it going to waste, but it's driving a lot of pollution into the waterways around San Francisco, the Delta area, a lot of pollution issues coming through that. So let's talk about and think about fixing both of them at the same time. So this is basically what we're looking at. We've got water generation, energy generation, super efficient distribution, and a massive increase. So we can start to talk about a new energy future. There is something like 77,000 gigawatt hours of electricity, unused potential on the roofs of California. So that's a big game. We also have a new networking future. Networks are traditionally built on root and branch architectures. With the NENA access pathway, we're now putting effectively a loop around every single block, and loops are connected to loops. And that means it's essentially indestructible. From an optical fiber point of view, it is indestructible because there are so many pathways between any points of A and B, and there is so much fiber there that you really can't damage it. From a power grid transmission, we need to be thinking in terms of research about more efficient, low impedance distribution networks. Nobody's done any work. I talked with an Australian power company. They've just spent nearly $3 billion upgrading their network, and they've still got 5% distribution losses, the same that they had. It's not good enough for the 21st century. One of the great research opportunities that's available is what do low distribution loss networks look like in a 21st century. So I think I'm going to have to click through. Health benefits. Imagine a world where we have clean air, we have clean water, we have low noise, we don't trip over on the footpath and fall over and break our hips. That's $1 billion cost to the health system in Australia alone. And we've got low toxicity in our natural waterways. Environmental outcomes, a path to a carbon negative. If we combine urban adaptation and rationalization, and we combine it with a process of defragmenting our natural ecosystems, by that I mean we carve around little forest pockets, we isolate them, effectively they die. So a process of reconnecting the forests, getting the urban environment working, stopping the drain of water out of the natural environment. Taking water out of the natural environment degrades the natural environment. One of the least understood and least recognized forcing mechanisms in climate change is that over the period where we've seen an increase in atmospheric carbon, it perfectly correlates with the buildup of dams. That we're concentrating water in dam systems, we're using that for agriculture, which doesn't store carbon in the environment, and we're removing from the natural environment the mechanism by which natural environments grow and sustain themselves. So, no power poles, beautiful footpaths, clean air, big trees, no pollution, no flooding. We retain water in the environment, we don't allow it to flood, we don't allow it to overflow sewage systems, lots of employment, all the big tech you want. It's a good thing, and a better economic future. The proposed financing model of this is that communities develop it as a property trust. You buy a unit in it. It might be the Capitol Hill South Infrastructure Access Unit Trust, but you buy a unit and you get a rate of return on that unit. That takes the funding burden away from central governments. It gives a new opportunity to invest in a high rate of return business for local governments. And if the community and the local government don't supply enough funding for it, then you open that up to pension funds and dedicated or specialist investments. It's a long-term, 100-year plus asset with a steady income stream, not reliant on the number of customers, it's reliant on the number of tenants in the system. Works better all around. This is details of economics which are basically show that in Australia, for example, we already pay around $175 per month for embedded passive access civil infrastructure. Poles, pits, pipes, trenches. Trenches dug 100 years ago are still at full book value. In fact, they raised them in value. So we're paying a lot of money, and this system costs in Australian dollars around $12,000 per household. It's got an income stream of about $1,800 just on the legacy utility services. If you're a legacy power operator, you want to move in because you're facing a massive upgrade. Our infrastructure, our cities are getting really old. From 1920 to 2000, they grew at about 18% per decade. So from 2020 to the end of this century, that urban access infrastructure over 100 years old is going to increase by 18-19% per annum. And it's going to start failing because the concrete and all the stuff they used in it just wasn't designed to last that long. And it is failing. So I think I've got to wrap up there, but quick one, lots of different layers of economic benefits. And I think I've said all that before. So thank you very much.
Good afternoon. My name is Lauren Cook, and I am from Carnegie Mellon University. I am a PhD candidate there in the Civil and Environmental Engineering Department. And today I'm going to talk to you about the other end, so having too much rain versus not having enough rain today. So first, I'm going to discuss with you why do we care about expected changes in rainfall. I'm going to give you a little hint. It's called flash flooding. Second is how can we use data from climate models to figure out how rainfall will change in the future? And finally, how can we use these changes in rainfall for future stormwater management design? So this is an example of a year in Pittsburgh in 2011. This is the daily rainfall. And I'm going to draw your attention to that little arrow. This is the annual maximum rainfall in Pittsburgh in 2011. And this rainfall caused a flash flooding in the area, which led to 4 fatalities. It was a very sad event. A family got trapped. So what did we do to resolve this issue? Well, we put up a sign, and this sign flashes when there's high water and says you cannot travel on this road. Now, some engineers would say this is a very good low-cost solution to prevent fatalities, and others would say that we would need to redesign the road since originally it was designed to be in a stream bed. So how do we currently design stormwater infrastructure today? Well, an older method is called the rational method, and what goes in is what we call a runoff coefficient, which is essentially the soil type. And we also put in the watershed area. And what else goes into this equation is something called the rainfall intensity, which I'm going to talk to you mainly about today. How do we get these rainfall intensities? Well, we start off with a historical record, and we usually take the maximum annual rainfall for the past 100 years or 200 years if we have the data. And we take this annual maximum and we create something that's called an intensity duration frequency curve, in which to this curve we're going to input the storm duration that we'd like to design for, and we're going to output a rainfall intensity, which again, we input into the rational method. From this equation, we can get something that's called peak discharge, which is the very top maximum point on this curve, which under the curve is the total runoff volume. And for those of you who are unaware, the difference in rainfall volume and runoff volume will be the amount of rain that is infiltrated into the ground. From this peak discharge, we can design things like culverts, or maybe even the stormwater management of the future, as the former speaker presented. But this is great. We have peak discharge. What else can we do with this? Well, we have another model, which is it's the EPA's model called the Stormwater Management Model. And with this model, we have the same inputs, soil type, watershed area, but a little more complex. But instead of using an intensity duration frequency curve, we use a rainfall time series. And we can change these time series to test different years. We can test a dry year. We can test a wet year or an average year, for example. And what we get out is going to be peak discharge or any discharge, but on a time series, so over a year or over a month, to see if our infrastructure can withstand the rainfall that we're inputting into it. So this is great. Any hydrologist will say they love the SWMM model, and if we could go on using this forever, then my talk would be over now. So what's the problem? Well, things are going to change. As you all know, rainfall patterns are expected to change in the future, and a term that we use in the field is called stationarity versus non-stationarity. And historically, we've assumed that rainfall will sort of look like this. It'll go up, it'll come back down, but the average will remain the same. And what we're starting to understand now is that rainfall will become non-stationary, and it'll go up, come back down, but in the end, the average will be increasing over time. So why is this happening? Well, climate change is upon us, and what exactly is going to happen? Well, we don't know, but we know a couple things. We know that wetter areas are going to get wetter. So for example, the green area shows that we will have a 10 to 30% increase in total annual rainfall. The drier area, the brown, is showing that we're going to have a 10 to 30% decrease in total annual rainfall. And we're not certain exactly what will happen, but we know it's going to change. So that brings us to one of the questions is, so what will rainfall look like in the future? Because we need this rainfall to design stormwater management in the future. If you asked me 20 years ago, maybe I'd say, well, it'll look like this. It'll look like historical rainfall. But if you ask me now, I'm going to say, well, maybe we'll have more rain days where it rains in the future, or we'll have less. Maybe we'll have an increase or a decrease in total rainfall throughout the year. Maybe we'll have more extreme storms, so that's more rain coming down at one time. Or maybe we'll have longer periods between rain, just like we're seeing now in the West Coast. This brings us to our research question, is how can we use this data from climate models to inform rainfall for use in stormwater design, or really in any type of design that you would need rainfall information? So we're looking today at a case study in Pittsburgh, and what is interesting about Pittsburgh is that it has very intense microburst storms, it has very steep slopes, we're in the mountains, and this leads to what I showed you earlier, flash flooding and fatalities. So here we are in Pittsburgh. This is what the case study area looks like. We have 33 rain gauges. We have data on a 15-minute interval. This is excellent quality data, very small time step. And we have it from 2004 to 2014. So one of these rain gauges, one of the 33, it looks something like this. Very long data set. And again, we have data like this for each of these 33 gauges. So what do we want out of this? We want the exact same data, 33 gauges, 15-minute, but instead we want it for two future time periods, 2040 to 2050, 2060 to 2070. How do we plan on doing this? We're going to use a model. Just think of it as a black box for now. We call it the change model. What goes in is the observed data. What comes out is two future time periods of rainfall. How are we going to manipulate this? We're going to use climate data. We're going to select two different climate models, which I'm not going to go into big detail, but I will bring to your attention that these climate models are on a 3-hour interval, whereas the data we have is a 15-minute interval. Now I'm going to tell you just a little bit more about the climate models before I go into what is actually within the model. So climate models, we have several types. The largest climate model is called your general circulation model. It models the Earth on what is approximately a 100-kilometer grid cell, about half the area of Washington, D.C. But this is still too large for us as engineers to use, so we need to do something that's called downscaling. And there's two types of downscaling. I'm not going to bore you with the details, but one uses physical equations, which is called your dynamical downscaling, and one uses empirical or statistical relationships, and this is called statistical downscaling. In the US, there's two different big data sources that have climate model data available. The NARCAP, which is the North American Regional Climate Assessment Program, and there's also Reclamation CMIP-5 data, which is your statistically downscaled information. Today I'm going to talk to you about NARCAP data. Why did we choose this NARCAP data? Well, because it's on a 3-hour time step, and this is the smallest time step that's available in the US for a climate model today. And also what I want to bring to your attention is that within this data set, there are 6 different regional models to choose from. During the research, we selected 2 of these, which were closest to the observed data. And I'm not going to go into this right now, but if you do have questions, I'd be more than willing to talk to you about how we selected these models. Now, I've talked to you a little bit about the climate models, and now I'm going to talk to you a little more about the change model that we're using. It's kind of intense, a lot of equations, so don't get overwhelmed by the details. I'm going to bring you back to the big picture at the end. So when you're building a model like this, you don't want to jump right into the most complex model. You want to start simple and you add complexity. Out there, one of the simpler methods is called the delta change method, and a more complex method for, again, building rainfall is weather generators. If you want to add complexity within each of these methods, you're going to look at different rainfall parameters. Again, these rainfall parameters we discussed before. You can have the number of rain days in a year, you can have total rainfall, you can have the number of days between rain, and again, all of these things are potentially going to change in the future, and all of these things you will have to apply to the rainfall time series you're trying to forecast in the future. So what I'm going to talk to you about today is a rather simple model in the grand scheme of things, although you can let me know at the end how simple you think it is. And that is the delta change method, and I'm going to be looking at intensity percentiles, so sort of the probability that we will get a certain amount of rainfall in a certain period. Step 1 is you want to select the time period that you'd like to have. And in our case, we are selecting a 10-year period. This comes from the observed data set that we have. Step 2 is you select your baseline time period from the climate models, which we selected to be 1990 to 2000, which is closest to the observed data, again, that we have. Our future time period, 2040 to 2050, looks like this. This is just the first future time period that we're selecting. Your next step, in order to be able to compare these two time periods, rainfall, you cannot simply compare the time series because you cannot compare day 1 to day 1 in the future because it doesn't make sense. So you have to rank and sort the data in order to compare the two. So first you rank the data with the highest rainfall volume in rank 1 and the lowest rainfall volume 0 in rank about 30,000. Next, you're going to calculate the exceedance probability, which is the probability that you will have a given, so for example, you can have a 1% exceedance probability that you will have about 0.25 inches of rainfall in that time period or more. It's a little confusing. Again, don't get lost in the details, but again, if you're interested, I can tell you more in the end. So now that we've calculated the probability of rainfall, which more volume of rainfall is less likely, we can now take the delta. In order to do so, you take the future, you subtract the current, and then you get the delta of the climate models. Again, this is the future climate subtracted by the current or baseline climate, you get a delta. And what this is saying is that for a 0.01 probability storm, this is a very unlikely storm, we're going to have an increase in volume of about 0.2 inches. And as you can see here, the more unlikely the storm, the more volume that we're going to get added on. This is an example of one climate model. Other climate models will tell you something different. For example, this climate model tells us complete opposite trend. As you have a more unlikely storm, it's saying we're going to get less rainfall. Different models, different trends. So, like I said, different models can give you different trends. You can have an increase in rainfall for a given exceedance probability, for example, the 1%. Or, for example, you could have a decrease in rainfall for a given exceedance probability. For example, here is about 0.2%. So what do we do when we have this added volume? Remember that we have this delta on a 3-hour interval. However, we want a 15-minute interval. We call this disaggregation, taking this big volume and putting it into smaller volumes. So here's our 3-hour delta, and this is, for example, for the 1% exceedance, we have this much additional rainfall. So we're going to find in the observed data, we're also going to find that 1% exceedance probability. And within this 1% exceedance, we have 8 periods of rain, 15-minute interval periods of rain within the 3 hours. What we do, we divide the delta by 8. Very simple method, and we're going to add it on to our observed data. You can do the exact same thing. If you're subtracting volume, you divide the volume and you subtract it off. Now that I've talked to you about what we actually do in the model, how we add the volume or subtract the volume, I'm going to talk to you about some of the results that we got out of the model. Talk to you about 2 main conclusions that we found so far, and we still have a lot more work to do. So don't get overwhelmed. Again, I'm going to explain this step by step. So first of all, on the y-axis, we're thinking about the observed data. So this is the historical data graphed. On the x-axis, this is the future data. So if you see an increase, so to the right, this will mean an increase in the future. To the left is a decrease in the future. Again, and each point is one of the 33 rain gauges and one of the climate models. So what we're seeing here is this is climate model 1, this is climate model 2, and they are showing opposing trends. This is very common in the climate world that we're seeing conflicting trends from the climate models, which is called uncertainty, and what we like to call is we have no idea what to do with this information. So opposing trends in the early time period from 2 different climate models, and there's many more climate models, so we could get even further opposing trends, but I'm not going to bog you guys down with that. Second conclusion that I want to bring to your attention is looking across time periods. So now we're looking at the 2040 to 2050 time period, and we're comparing it to 2060 to 2070. So as we move along in the future. So this is the first climate model that we saw, again, in the early time period, which is to the left, saying we're going to have a decrease in total rainfall. However, when we move on to 2060 to 2070, it's saying we're going to have an increase in total annual rainfall. And this increase is a 7-inch increase in total rainfall over 20 years. And this 7-inch increase could be the difference between over-designing and under-designing your culvert or your infrastructure. Finally, the second climate model, what is interesting is that in the late time period, 2060 to 2070, it's also agreeing with this first climate model and saying that we expect a 5-inch increase in total rainfall in the late time period. So as an engineer, we want concrete numbers. We want, oh, well, what's the probability that this is going to be accurate? Tell me some numbers, tell me some statistics. And the problem is we don't know. We cannot assign probabilities to each climate model because they are uncertain, because we do not know what the probability of them being accurate is. So we no longer have these fundamental principles of what's the expected value, just use the average. We don't have that anymore. So we're going to have to either design for the worst case or somewhere around in that area. So to close today, I want you to take away 3 big messages. First of all, rainfall is changing, and we have to figure out how to look at rainfall on a small scale. And the delta change method is one way that we can take climate information and bring it down to a smaller scale. We can create these rainfall time series using the delta change. However, we're still going to get varying results. One model will say we're going to get more rain, one will say less rain, and some will say that we're going to have an increase and then a decrease, or a decrease and then an increase over time. So since we have these different futures, we have conflicting trends, we have different scenarios, we're going to have to plan for all futures. We can no longer take the expected value. We have to completely rethink how we design, and we have to rethink how we add up these numbers. One strategy we're starting to research at Carnegie Mellon is called minimizing regret. And this involves minimizing financial regret. You want to minimize fatalities, which cost a lot of money, but you also want to minimize the cost of your infrastructure. With that, I'm going to talk to you about robust decision making, which we call the next generation of decision making, keeping with the theme. Again, cost-benefit analyses using the average. These are outdated. We don't know what the percentage of probability is in the future. So what we have to do is we have to learn. So we have to learn from the climate models, learn different scenarios. We have to design some type of infrastructure. And since we have several different scenarios of the future, we're going to test this design over and over again. And when this design fails, we're going to have to redesign it and revise it. And then we're going to have to design again. And then we'll test. And eventually we'll reach a point where we've minimized lives lost, and we've also minimized cost as much as we can. And we call this robust decision making with an optimality criteria of minimizing regret. That concludes my presentation. I'm looking forward to having some questions later. I'd like to acknowledge my funders and all the people that have helped me prepare this presentation today. Thank you.
This is to Mr. Dixon. My name is Alice Labrie, and I'm former U.S. Department of State Foreign Service. I live in New York City in Harlem on the Harlem River, where we experienced, was it Hurricane Anna? I forget their names. We got flooded. We are now considered an evacuation zone. And our bulkhead piece fell in the river. Anyway, this has to relate to when I joined the Foreign Service. My first assignment was in Turkey, Ankara, And I learned from a fellow newbie who was an engineer, later assassinated on duty. The pipes in Ankara were laid next to each other. I think he said the sewer pipes and the water drinking, which helped account for our intestinal disorders in Turkey. So I'm just curious to know, is Turkey a client, or what did that mean?
The fact that
they're
co-locating them. Co-location is probably that it happened to be convenient or they happen to have an open trench at the same time. There is a lot of variability about how people have done things around the world, and the Turkish infrastructure is probably really old. So one of the major problems that we're looking to address is structurally separate the flows of urban rainwater to stop it flooding sewage systems. And because that's one of the primary sources of biological contamination leading into intestinal diseases and major health issues. So urban environments are designed to channel water. For most of the last century, we viewed stormwater as a risk to the urban environment because we concentrate it, we accelerate it through that environment to get rid of it. And so when you do get flooding, you've got a huge volume of water flowing. So one of the challenges is to introduce urban storage, and we need intelligent systems to manage that storage so that it acts like a sponge.
So it had nothing to do with being located close to each other, it's just what it was taking in.
No, you'd find that probably the sewage system broke one of the other of the pipes, or sometimes you get people will use a sewage system as a stormwater system. Oh. And I was hearing a story about that in America.
We do that in America too?
There is one location I was told about yesterday. You shouldn't do it. It's not a good design solution, but it really goes back to the days where we just threw everything in the river. So one of the great, if there were a research thing that we could develop to really, really save the world, would be to take water out of sewerage. It is one of the most ridiculous pieces of science and physics that we take something which is about 350 grams in size and we mix it with 6 kilograms of water to move it somewhere else. So we take a small fecal problem and turn it into a really big one. If we could take water out of sewerage, it would be a huge revolution. But that's probably was the problem. Co-location, one system breaking, two systems getting overloaded, etc. You're welcome.
Hi. A comment also and a question for you. That very last point. Chris Rogers, University of Birmingham in the UK.
Yeah. Hi, Chris.
Hi. The zero water sewerage system has been researched in the UK, so it's something that I believe there is a potential for. But I was really taken with your system.
Thank you.
Really interesting. I want to spend a lot of time talking to you aside from it. But the question really comes back to this issue of if you put high voltage cables into the ground, then you need in some way to remove the heat. So we've been doing some work on long distance, shallow buried or shallow inserted cable systems, but we had to use forced cooling in some sort of way. So is that then built into your...
Yes, and one of the good things, first of all, is when you put cables underground is that you remove them from, like the atmospheric temperature. So it's under, say, a 200 odd millimeter thick precast concrete lid. So you then have, it's an internal structure. So we now have a defined space. So it's about, the power channel is about 250 mils wide by about 750 deep. So we have a pretty small, like 0.2 of a square meter cross-sectional area. And the average circumference around a block in Australia is about 800 meters. So that gives you an idea of the volume. Now, two things about that is that if you're in North America, you want that heat because you want to take that heat and use it to keep the water warm, so you avoid freezing. So there's one instance, say, in North America where you can get a compatibility element in the co-location. But also is that now we've got water systems which are essential ingredients in heat exchangers, and we've got water storage. So the idea of managing heat in the urban environment now becomes much easier. We've got instrumentation electronics, IT, water, and electricity systems, all where you can plug things into them, basically. So you can get all three. So if you're building a mobile network, for example, you need optical fibers and you need power sources. If you're managing water in an urban environment, then you need pumps and systems like that. So, but yes, you can take the heat out, and that is an essential element in low resistance networking. And that's the big black hole that nobody's really looked at for forever, really.
Yeah, okay. I've been banging on about multi-utility tunnels for a long time, so really take it.
Thank you.
For the second speaker, I really appreciated your talk and you walking us through the model and everything. It's very instructional. But in some ways, the results of your study sort of cast doubt on the very scientific models that many scientists use to prove climate change is happening. And I'm not a climate change skeptic, but one might say that the inability to prove a trend using different models is the reason for skepticism. And because of the expensive costs of renovating infrastructure, as Guy pointed out, it's a reason to not change infrastructure rather than take the most drastic measures. So.
Is there a question in there somewhere?
What would you say to reinforce people's confidence in those models upon giving you contradicting conclusions?
So a lot of the analysis that we've done for climate change is based on observed trends. So we can see from observations, not from forecasts, that temperatures are rising and that rainfall patterns are changing. And we use climate models to observe future trends to try and figure out, well, how much changes are we going to see in the future? So to answer your point of we should just do nothing because we don't know what's going to happen in the future, well, this is not an option. We know something will change, and we know that even now the infrastructure that's currently being used is not fulfilling the needs of the current climate. So in order to even keep up with what's happening now, we should still start investing in infrastructure of the future, especially since the lifetimes are 60 years or longer. Since we don't know what to expect in the future, we need to start investing and planning now so we can help to account for that.
Yes, I have a statement, actually a follow-up, and then a question for Dr. To be Cook. First of all, I just want to comment on your question. I think it's important to make a distinction between our current inability to predict the future impacts or outcomes of climate change versus our ability to determine that climate change is occurring. I think what she was discussing was the fact that there can be a broad spread in the prediction of the outcomes of climate change, but that doesn't necessarily lead to arguments about whether climate change is happening. So that's my statement. My question is, even though that there is considerable uncertainty in the various predictive models, this is a second order question, therefore, because that's sort of a first order problem in the approach. Why did you choose as a baseline only a 10-year period?
So we only have observed data for 10 years on that 15-minute time scale. Okay. We have longer data sets of 100 years, but it's on an hourly interval. And for the stormwater management model, we need that very small time step. And in order to model that small time step in the future, we need the observed data that's on this smaller step.
So I think it's important to take the higher fidelity data, but I'm curious, have you compared the 100-year lower fidelity data with the 10-year, 15-minute data and see how it overlays over that 10-year period? Or did you not collect, when we shifted to a higher fidelity collection system, can you not map the lower fidelity in the same time period?
So it's difficult. The longer time period data is collected solely at the airport,
Okay.
and we want the data for the entire kind of
Okay, so
Allegheny County.
it's not only the time interval, but it's also the spatial fidelity.
Exactly.
Okay.
Exactly.
Very good. Thank you.
If I could just add one quick comment. We live in a world of climate uncertainty. So if you don't know exactly what's going to happen, you as a designer, you need to be encompassing a broad range of issues. So for example, we don't know next year whether the drought will break in California. It may well do, and I hope and pray that it does. But in this environment of uncertainty, we need to be looking for solutions that solve many problems. No point banking on one thing, focusing just on, say, atmospheric or temperature rises, when at the same time you're running out of water. So you need to try and capture economies of scope in your design and solution set. So in the case of the pathway, we're saying we need better power systems, we need better optical fiber systems, we need better water systems. If you can incorporate a range of problems into one solution, then you're going a long way to dealing with a lot of the elements of uncertainty that we face.